Oh, hi there, it's Mrs. Bertrand, and this is Balancing Equations. Balancing equations is based on the law of conservation of mass, and this just states that matter is neither created or destroyed. This means that the total mass of reactants equals the total mass of products in all situations. This includes in nature, in our chemistry lab, and therefore on paper in our chemistry classroom. Balancing equations just means that when we're working through an equation, we have to make sure there's the same number of elements on each side of an arrow. We can do this by using coefficients, and coefficients are always in front of a chemical species. We cannot change subscripts. So for instance, let's say I had CO2 and I suddenly wanted to have 2 carbons. I can't just put a 2 here because that now is not carbon dioxide. What I would have to do is I would have to start with CO2. That formula must be maintained, but if I want 2, I can put a 2 in front. 2 in front means 2 times whatever number I've got. So in this case, I would have 2 carbons and 4 oxygens. Let's have a look at some balancing rules. The first thing that we should do is count the number of each element on each side. We can do this formally or informally. Lots of students will start doing this in their heads after a while, and some students will do this on paper and work it out. I'm going to show you how to do it on paper so you can use that as you need it. Polyatomics you can use as groups and count them as groups. Putting brackets around polyatomics that don't have brackets is key here. Another hot tip is water can be written as HOH, and we would do this if we had hydroxides on one side of an arrow and water on the other, just so you can count hydroxides as groups. You don't have to do this, it's just another hot tip. Usually I would use oxygen and hydrogen as my last thing to balance as well, and that's because anything that is a Hofbrinkel like H2 and O2, these are the most common ones we'll encounter. If we put a coefficient in front of either one of these, we're only changing that one element and not multiple elements that we do when we have a coefficient in front of a compound. Speaking of Hofbrinkels, we can also balance them using a fraction. And I know what you're thinking. Fractions! I hate fractions! But fractions are your friends when we're balancing. Because when you have a Hofbrinkel, Hofbrinkels always have a 2 in the formula. If I wanted to have an odd number of hydrogens, how do you times 2 an odd number without getting into decimal places? We don't want to do decimal places, but we are allowed to use fractions. So anytime we want an odd number in front of a Hofbrinkel, you're just going to put that odd number above a 2. So let's say I wanted 7 hydrogens. You would take 7 and put it over 2. And this is because 7 halves of hydrogen, which is an H2, that means your 2's can cancel, leaving you with 7. Let's try this again. What if I wanted 11 hydrogens? I hope you're yelling at the screen. Use 11 halves. Yeah, 11 over 2 is your fraction. What if I wanted 19 hydrogens? I hope you're saying use 19 over 2, because that's exactly what you would do. See, fractions, so easy. Everyone loves fractions. One tricky bit when we're doing our balancing is that sometimes we have more than one source of an element. For instance, we might have CO2 and water, let's say on one side of an arrow. Notice that there's oxygens here and here. When this occurs, we have to add them together for a total number on that side when we're doing our balancing. So we'll look at all of these different scenarios with some examples here. Let's start with a bit of an easier example, a good place to start. And I'm just going to start by showing you that process of counting on both sides. And the way I do this is I just count from left to right and I just pull out the different elements we're going to have to count up. So the first element I'm reading from left to right is cesium, and then the second one I see is nitrogen. And I'm just going to count. So cesium on the left I have 1, cesium on the right I have 3. Nitrogen on the left I have 2, nitrogen on the right I have 1. I would start with our nitrogens first, and that's just because cesium is the easiest one to balance because it's only just one cesium here. Although you can balance cesium first, then nitrogen, it doesn't make any difference. You can always change your mind and go back and forth with your balancing. Let's have a look at our nitrogen since we decided to do that one first. Right now I have 2 nitrogens on the left, only 1 on the right. The only thing I'm allowed to do is put something in front of a compound. That number multiplies everything behind it. So I right now I have 1 nitrogen, 1 times 2 will give me 2 nitrogens. That will also change the number of cesiums. That's going to be 2 times 3, making 6 cesiums. Not a big deal because I had to fix them anyways. It just means that when I go and fix them on the left-hand side, I'm now going to put a 6 here because 6 times 1 makes 6 cesium. And then everybody is happy. Huzzah! All right, let's step up our balancing game here. We've got magnesiums. Let's count, actually, you know what I'm going to do before that? I'm going to put a bracket around my polyatomic so it's easier to count. Now I'm going to start counting. So I've got magnesiums on the left and right. I've got hydrogens. And here's where putting a bracket around my group allows me to count things as groups. Now I could separate this into N's and O's, totally fine, you're allowed to do that, but I find it's quicker to do it as a group, so I'm going to show you that strategy. So magnesiums on the left we have 1, magnesiums on the right we have 1, hydrogens on the left we have 1, hydrogens on the right we have 2, I think I said right there twice, but just ignore me. Left and right. Nitrates on the left I have 1, nitrates on the right I have 2. Let's start with our nitrate groups. Hydrogens, because hydrogen is a standalone on the right-hand side, usually easier to balance that one last. So let's go ahead and do nitrates first. I have 2 nitrate groups on the right, 2 in front of this compound. We'll do 2 times 1, making 2 nitrates on the left. That also does 2 times 1 hydrogens. And look at that, I just balanced 2 things for one amount of work. And that's a good show. That often happens, so don't be surprised. Oh, what happened to my arrow? I'll just put that in there. All right, this is an example of where water and hydroxide are part of the formula on opposite sides of an arrow. So to show you what you can do, you can totally balance it as is. I'm going to show you a different strategy by taking water and writing it as HOH, and then keeping everything else the same. So again, this is just an option. You totally don't have to do this. Let's count everything as usual. Calciums, hydrogens, and this time I'm going to count hydroxides. That's the whole point of taking water out of its H2O form, is so I could count hydroxides. So calcium's on the left, we have 1. On the right, we have 1. Hydrogens, watch out. I've got 2 sources of hydrogen. I have to add them together. So I have 2 plus another. I have 3 hydrogens on the left-hand side. On the right, I just have to consider the hydrogens by themselves, because remember hydroxide, although it has hydrogen, I'm going to count them as a group. So I have 2 hydrogens over there. Hydroxides, I have 1 on the left, and I have 2 on the right. Typically, I would say let's do hydroxides first. They're the most complex, so try to get them done and over with. I've got 2 on the right. Let's make 2 on the left. So 2 times 1 hydroxide makes 2 hydroxides, and 1 times 2 hydrogens. Again, I'm going to consider all of my hydrogens, so I have 2 plus another 2 now, so I now have 4 hydrogens. Again, that's the 2 here plus the 2 here, making my 4. On the hydrogen side, I do have to fix up on the right now. Pretty simple fix though, because I want 2 hydrogens to become 4. 2 times 2 will make 4. Now everybody's a balance, and I'm a happy camper. All right, the last one, everyone's favorite, the fractions. At first you're going to be like, I hate fractions, but I'm telling you, they're your friends. You're going to love them. Let's do the same as usual, count up our elements. So we've got C's, H's, and O's. C's on the left are 4, C's on the right is 1, H's on the left is 10, H's on the right are 2, O's on the left are 2. Here's where it gets a bit tricky again with O's on the right. We've got 2 plus 1. We have 3 altogether. I would start with our C's and then do O's last. And the reason I do O's last is because we have a standalone O, and they're always easiest to fix. So let's start with our C's. We have 4 on the left, we want 4 on the right. 4 times 1 makes 4. On the hydrogen side, we've got 10 on the left, we want 10 on the right. Right now we have 2, so 2 times something must give us 10. 2 times 5 will give us our 10. Oxygen's got a little complicated here because we have 2 times 4, 8 oxygens here, and 1 times 5 over here, for a total of 13 oxygens. So when it comes to oxygens, I have to have 13 oxygens on the left since I have 13 on the right. I hope you're all shouting at me. Use a fraction. They're so great. All we need is to do 13 over 2. You're so right, everybody. Great job. 13 halves. Now, if you didn't like fractions, I can't imagine this being the case, but let's just pretend in some crazy world you don't like fractions. You can get rid of your fraction. You just have to multiply everything by 2, the entire thing. So you could have 2 C4H10s. 2 times 13 halves is just 13, but by fraction. 2 times 4 is 8 CO2s. And 2 times 5, 10 H2Os. So if you don't like fractions, you don't have to use them. I don't know why you wouldn't, because you're a crazy person, obviously. But, obviously, if you don't want to, that's your prerogative. All right, time to have a super fun time doing homework. We'll start with a worksheet, actually. And then these are some additional problems that you can do just for some extra fun times with balancing. Have fun, yippee!